Welcome back, ladies and gentlemen. In this video, we'll talk about impulse and momentum. And momentum is one of those quantities of motion that you can think about as how much motion an object has. For instance, if you are looking at standing in front of either a train or a Nerf bullet, and each are traveling at the same speed, which one would you rather get hit by? So momentum is a vector quantity, so that means that it does have direction. Its symbol is p. That's because the m was taken by mass. P has Latin roots to it. I think it's pater or something like that. You can look that up. The equation for momentum is just mass times velocity, or p is equal to mv. Okay, the units are kilograms meters per second. And that P equals MV, that's a formula that you will find on your formula sheet. So it's one that gets used with our questions quite a bit. Okay. So here is an example. Find the momentum of each object. So if we have a 25 kilogram artillery shell going 600 meters per second, that's just going to be taking the mass, which has to be in kilograms, or in this case, 25 times 600. And if we plug and chug that, we find that the momentum of our artillery shell is 15,000 kilograms meters per second. And that little, I'm using a little dot there. That's just a dot to represent multiplication. So that's kilograms meters per second is the unit for momentum. In the other side of our screen here, a 900 kilogram Honda Civic is going 50 kilometers an hour. Well, the first thing I'm going to do is I'm going to take 50 kilometers per hour, and we're going to need to divide that by 3.6 to turn that into meters per second. So that ends up as 13.9 meters per second. And there are some other, later we'll look at different times for things, and you just want to make sure that your time is in seconds and your velocity is in meters per second, standard units like we've done before. Okay, so the momentum of this Honda Civic going 50 kilometers per hour would be the mass of it, which is 900 times 13.9 meters per second, or 12,500 kilograms meters per second. And if I'm thinking about which one of these objects I'd rather stand in front of, I'll be honest with you, I'd rather stand in front of neither. Both those are pretty massive momentums. If we think of a car traveling along the highway or an artillery shell, I wouldn't want to be in front of either one of those. So those are two large momentums, two large momentum examples. Okay, so we often will look at the change in momentum and what is required to change the momentum of objects. So when we talk about change in things, we're talking about just the difference between the final and the initial quantity. Okay, so that's just final. So change in momentum is final minus initial momentum. Okay, so we can use some symbols to describe what we're talking about. And if we keep working through, we can get to a point where we have delta P is equal to M delta V. This is a formula that is on your formula sheet as well. And here's an example for us to look at with that. So if we have a 145 gram baseball is thrown towards a batter at 30 meters per second, hit back towards the pitcher at 50 meters per second, find the ball's change in momentum. So I did try and use some realistic numbers here. So I looked up the mass of baseball, and it is 145 grams. So when I write that number down in my knowns, I'm just going to make sure that I'm writing that number in kilograms. My initial velocity here, if I'm thinking about this ball is going to have an initial velocity coming towards the batter, and then its final velocity, if I think about it, going back in the other direction. One of those numbers is going to have to be negative. So I'm going to call my initial velocity positive. So my positive direction here is going to be to the right. So my initial velocity would be positive 30 meters per second. My final velocity then would be negative 50 meters per second. And what I'm looking for is change in momentum. So I'm just going to put delta P here as my unknown. Okay, so my formula that I'll use is delta P is equal to M delta V, or my mass is 0.145 kilograms. My delta V is my, maybe I'll squeeze that in here. That's my final velocity minus my initial velocity. So final is negative 50 minus my initial, which is 30. And we do have to kind of be tricky of signs in here. So you just have to be mindful of your signs and make sure that that we're finding the change accurately. Okay, so if we plug and chug this, 0.145 times negative 80, we should get a change in momentum of negative 11.6 kilograms meters per second. Put a box around this thing because that's what we are looking for. Okay, and this question is done. Now, the next thing that we'll look at then is what is required to change momentum. Okay, so if we have a dad pushing a kid on a skateboard, what's required? We all know that to change the velocity of something, what do we need? We need force. May the force be with you. Okay, so a little bit of formula derivation for you. So we've been working before with an unbalanced force that is going to be equal to the mass times acceleration. If we apply a net force, it is going to change the velocity of something. And if we change the velocity of something, we'll change the momentum of something. So that's where we're heading with this. So F is equal to ma. This is our formula for acceleration. Now, if I multiply both sides by delta t, or the amount of time, this thing here is something special to us, and that is impulse. So that's what we'll be talking about next. So if we apply a force for a certain amount of time on something, it is going to change the velocity of something. Okay, so impulse. To define impulse, it is a vector. It has no symbol. The equation for impulse is just force times time. Okay, so or impulse is equal to F delta T. Okay, so F delta T we'll see on your formula sheet as well. So when you see that, that just means impulse. And the units for impulse is or are Newton seconds. Okay. Okay, and why is that special to us? Is because impulse is equal to the change in momentum. If you apply a force to something over a certain amount of time, it is going to change the momentum or change the velocity of something. Okay, so then if we write that formula out a little bit, F delta T is equal to mass times your change in velocity. And if you have a look at your formula sheet, this is another formula that you will see on there where impulse is equal to change in momentum. So applying that to things like airbag design or in this case, an egg that we're trying to keep alive. So this is something that this concept is something that engineers think about all the time, right? In car crash or car design, our whole objective here with an airbag, with this crash test dummy, car smashes into something, its final velocity is going to be zero. Its change in momentum, is going to be the same. If a car is traveling at 50 and 50 kilometers an hour and it's going to end up crashing into something, it ends at zero. What car designers do is they try and increase the amount of time. They try and increase this amount of time. They try and increase the time so that the force is going to decrease. So the amount of force that is going to be put onto a human body is going to decrease. Okay, so same with an egg. If you look over at this right-hand side, and this is from a video called "Understanding Car Crashes," which I'll post a link to. It's a neat video just looking at how engineers use the concepts of physics to design cars. So if we think of throwing an egg against a wall, you're going to have a very short amount of time that an egg is going to run into that wall. So in that short amount of time, that means your force is going to be huge and that egg is going to break open. But if you throw an egg into a sheet, you can see you just extend that amount of time to bring that velocity down to zero. More time, less force, less breaking things. Okay, so another way that you will see impulse in, and we would have done this in greater detail in the classroom, is looking at the area under a force time graph. So if we look at this as being force, or units are down here, right? This is force in newtons and then time in seconds. A way that we can find our impulse of or on an object would just be finding the area under this curve. So in our case, our impulse on this object would be 1/2 times base times height because it is a triangle. And we could say, hey, or find that this thing has an impulse of 1.92 Newton seconds. Okay, so in our next example, what if we have, if we look at the baseball in the previous example and we look at that bat and ball being in contact for 0.7 milliseconds, how much force did the bat apply on the ball? So just a comment here is, well, first of all, we are going to apply impulse is equal to change in momentum. We already know what that change in momentum is going to be. We solved that before. That's going to be 11.6 kilogram meters per second. Okay, the amount of time here is given as 0.7 milliseconds. So just a quick comment here on milliseconds. We need to turn our time into seconds, so this will end up being, we have to move our decimal place 3 times to the left. Okay, so 3 times to the left, our time of contact for this bat and ball. It's going to be a tiny amount of time, right? We can all imagine that. It's going to be a fraction of a second. And what we're going to be looking for is the amount of force that's going to be on that ball. Okay, so if we substitute our time into our equation, and then we plug and chug or divide both sides by 0.0007, we get that our force is equal to negative 1.6571 newtons, or force is approximately equal to negative 17 kilonewtons. Okay, and that negative, the negative just indicates that that force is acting to the left, right? So this is force acting to the left, acts to the left. Okay, and that's because in our previous example, we talked about the positive direction being to the right. So that makes sense. We're going to have to apply a force acting to the left to make that ball fly back to the left. Okay, so here is one for you to try next. Really, it's just questions from here are just going to be looking at derivations and solving for different things within our impulse equals change in momentum formula. Okay, so here's an example for you to try. If we have a 38 kilogram kid, he's cruising on a skateboard at 2.1 meters per second. So their dad is going to come along, give them a push with an impulse of 95 Newton seconds in the direction they were going. So here's a kid that has some velocity. Then dad comes along, gives them an impulse. That's an F delta T is equal to 95. What is going to be the new velocity of the kid? Okay, so we're going to be looking for the new velocity where our initial velocity was 2.1. Okay, so go ahead and try that out. Plug in your answer. Okay, and then practice for you is momentum and impulse worksheet questions number 1 to 9. Thanks, folks, and we'll see you again soon.